Next is logic families. So by logic families, we have different types of logic families uh, for the different gates we use. The most popular are the TTL or the transistor logic. CMOS, or the complementary MOSFET. MOSFET is metal oxide semiconductor field effect transistor. MOSFET is also called as MOS. That is why it's the short form for MOSFET. Um, then you have ECL, emitter coupled logic. There are many more, but mainly we'll be dealing with these three. Okay, so first we'll deal with the CMOS logic. So we'll be studying about. So when it comes to a particular gate, that is, you have these gates inside a IC. Now what is an IC? IC is integrated circuit. Okay. So what do you mean by integrated circuit? It is an integration of different circuits. Integration of different circuits. Integration means what? Summation of different circuits. So inside an IC, you have many circuits integrated inside this. That is what you call as IC or integrated circuit. So broadly classified, you have digital ICs and analog ICs. So in this particular subject, we'll be dealing with digital ICs because the subject itself is digital. So when you consider a particular logic gate, suppose you are dealing with a Nand gate. Okay, so suppose this is a 2-input Nand gate. Okay, this is your output. Now when you give an input to A and another input to B, you get an output Y. So suppose you are giving A equal to 0 and B equal to 1. So the output should be 1. So when you apply these inputs, it takes a particular small amount of time for the output to change. That is, according to the input, the output should change. Suppose this is 0, 1 and my output I am getting is 1. Okay. So now I am changing my inputs to, say, A is changed to 1 and B is still at 1. So my output should change to 0. The output was 1 at first. Now it should change to 0 when I changed my input A. So how fast does this Nand gate respond? What is the time it takes for the gate to respond to a change in input? Or what is the time it takes for the output to change when there is a change in input? That is called as propagation delay. Okay. So when there is a change in input, there is a change in output, and the time it takes for the output to change when there is a change in input is called the propagation delay. Now, I told that this is a 2-input NAND gate. Now, any gate, not IC, any gate, it can handle so many inputs. Okay, there must be a limit to the number of inputs that can be connected to a particular gate. So the number of inputs that can be connected to a particular gate is called as the fan-in. Number of inputs that can be connected to a particular gate is called the fan-in. So in this case the fan-in is 2. Only 2 inputs can be connected. So if you have a NAND gate with 3 inputs, 3 input NAND gate, you can connect 3 inputs there. Now, suppose you have a NAND gate and to the output of this NAND gate, I am connecting many other gates. Okay, some gates. I am connecting this to different gates. You have inputs here. This is a gate, some gate, not necessarily be NAND gate itself. It is some gate, and connected to that particular gate you have many other gates. So when you consider one particular gate, one of these gates, I told that I am applying 1 or I am applying 0 to a particular gate input. Now, how do I consider that as a 1 or a 0? That depends on the voltage I apply. So 1 does not necessarily mean 1 volt or 0 does not mean 0 volt. 1 means above a particular voltage. You have a threshold voltage. That depends on the logic family again. So suppose I am saying any voltage, just assume. Okay, this is not any typical value. I am just assuming. Any voltage greater than say 3 volt, I am considering as 1. It's an assumption. And any voltage less than say 0.5 volt, I am saying as 0, high and low. So that also means that for this particular voltage to be considered as a 1, so much current should flow into the input of this particular gate. Minimum 3 volt should be applied so that it is considered as a 1. So there will be a particular current associated with this 3 volt. Above that, the current will also increase. So minimum so much current should flow to the input of a gate so that that particular voltage is treated as a 1. And the current flowing through an input should not exceed a particular value, should be less than a particular value so that it is treated as a 0. So keeping that in mind, coming to this particular gate, when I apply some inputs, has a current flowing out. This current, you know that it will split. These currents, splitting currents, are entering the inputs of these gates, because the output of this gate is driving the so many gates. So I output may be associated with a 1 or a 0. Suppose you have a logic 1 here. So you have a high current, a particular current here. So logic 1 means this current should be minimum so much value. Suppose I am taking an example, just an example. This is logic 1, and suppose this is say 5 milliampere. And I am saying that minimum 1 milliampere should flow into the input of a gate so that it is treated as a logic 1. So this gate output is connected to many gates. The output is a 1. Input is given such that output is a 1. So that means what? 1 is applied to the input of all these gates. So it is shorted and given to the input of all those gates. But just because you gave the voltage, that is not sufficient. Minimum this much current should flow to the input of these gates so that it is treated as a logic 1. So I am saying that minimum 1 milliampere should flow to the input of each of the gates, minimum, so that that particular voltage is treated as a logic 1. So here suppose 5 milliampere is flowing. Minimum is 1 milliampere. It can be more than that. 5 milliampere you have at the output. So this will split. All the gates are same. So if the load resistance is same in each case, suppose it is equally splitting. So you have 1, 2, 3, 4, 5, 6 gates. So 5 by 6 will be the current through each of these. That is not equal to 1 milliampere. So how many gates can be connected to the output of this particular NAND gate so that each gate gets a logic 1 at the input? In order to get a logic 1 at the input of each of the gate, 1 milliampere should flow. So it should be only 5. So that is called the fan out. Fan out is simply defined as the number of gates that can be connected to the output of a gate so that the operation does not change. Logic does not change. That is, if the output of the gate is a logic 1, the inputs of all the gates connected to the output should also get a logic 1. So much current should flow to the input of each of the gates. How many gates can you connect like that to the output of this particular gate? That is called the fan out. So fan in is the number of inputs and fan out is the number of outputs of this particular gate in this case. That is simply put. Input is fine, but output, it has a complication that you can't just simply connect any number of gates to the output of a particular gate. The current should be considered. So that is fan in, fan out and propagation delay of a particular gate. Noise margin is the maximum noise signal that can be added to the input signal of a digital circuit without causing an undesirable change in circuit output. So what does that mean? If you have a digital circuit, suppose this is a digital circuit. Okay, this is a digital circuit. You have inputs and to these inputs some noise comes in. We know that in a digital circuit the voltage is very low. That is 1 volt is, like we assumed, greater than 3 volt or something. So it's as small as that. So it's very easy for the noise to come in. Okay, so if a noise is somehow added to a particular input signal, how much noise can be added to the input signal so that the normal working of the circuit does not change? That is, suppose to this digital circuit I am applying a 0 and a 1 to the inputs and some noise is added to this. Suppose the noise signal is so high that this 0 volt is changed to 1. Then the normal working of the digital circuit does not happen, because this is treated as a 1 instead of 0. Actually we are giving a 0, but due to the noise, due to the addition of noise, the 0 changes to 1. So there is an undesirable change in the circuit output. So that is noise margin. How much noise can be added to the input so that there is no change in the output. This is treated as a 0 still, and the output depends on the 0 and 1 only, even if there is a noise. So how much noise can you add to the input so that there is no change in the response of the digital circuit? That is called the noise margin. Now we talked about the propagation delay. Now Suppose this is 50% of the whole thing. This is logic 1. This is logic 0. This is the 50% of this entire thing. This is logic 1. This is logic 0. Now, suppose this is my input and this is my output. Suppose it's a NOT gate or something. I'm giving an input. And practically, when you give an input, it does not rise very fast. Like we say this is 0 and this is 1. So in practical circuits, this may not be the case with the input and output. That is, we may not get ideal voltages. We may get voltages like this. That is, from 0 to 1, it is taking some time to rise. Not like this instantaneous rise. And in order to change from 1 to 0, it may not fall instantaneously. It will take some time to fall. So suppose this is my input and this is the complement of that, the output. So here you can see that it goes from 0 to 1 or low to high. It takes some time to rise to high. And ideally for an inverter or a NOT gate, 0 complement is equal to 1 and 1 complement equal to 0. So 0 complement should be 1, but here since it takes some time to rise, it is still remaining high, though it should have fallen. And this is the time it takes to fall. And this is the time it takes to rise because of this fall. So this from here, this 50% to this 50%, this time is called as propagation delay to change from high to low. High to low is for the output. We are talking in terms of the output. The time it takes for the output to fall from high to low is called TPHL. And due to a change in input, there is a change in output here. This is from low to high. So that is TPLH. Time it takes for the output to change from low to high. These are calculated at 50% values of the high of the input and the output. Those are called TPHL and TPLH, propagation delay. Time it takes for the output to change from high to low and output to change from low to high when there is a change in input. And the propagation delay, the total propagation delay of the gate, propagation delay TPD, is the average of these two, TPHL plus TPLH by 2. This is propagation delay. Next is power dissipation. These are some of the terms related to the logic families. So we are just defining these terms first. So power dissipation, it's the power required by a gate to operate with 50% duty cycle at a specified frequency. Power required by a gate to operate with 50% duty cycle at a specified frequency. And duty cycle means what? On time, or the time it's you can say high divided by high plus low. This is the actual duty cycle, but in the case of digital we can say that it is high by the time it is remaining high by time it's high plus time it is low. That is, suppose this is my input or output, this is my high or on, and this is my off. So this divided by the total time is called the duty cycle. 50% duty cycle means T on is equal to T off. So you get T on equal to T on plus T off means 1 by 2. That's why it's called 50% duty cycle. So power dissipation, it is defined as power dissipation is defined as VCC into ICC average by N. VCC is the power we give for the IC to work. Usually it is 5 volt. ICC is the current derived from the VCC, from the power supply. Average current divided by N, where N is the number of gates in the IC. Why do I say number of gates in the IC? Normally, if I take a 2 input Nand gate or NOR gate, OR gate, AND gate, all those, you have 4 gates inside an IC. Likewise, the number of gates inside an IC will change depending on the type of IC it is. So you don't have a single IC single gate inside an IC. Normally you have multiple gates inside an IC. So N is the number of gates inside an IC. And ICC average is ICC H, that is high, plus ICC low by 2, or the average of ICC high and ICC low, where ICC H is the current drawn by the IC when all the gates in the IC are in high state. Suppose you have 4 gates inside an IC and all the 4 gates are in high state. So that is the extreme condition. All the gates are in high state. All the gates are in high state means all the outputs of the gates are in high state. 4 gates you have inside an IC, all the outputs are in high state. So that is the maximum current that can possible that is possible inside that IC. All are in high. maximum current. So that is ICCH. ICCL is when all the gates inside the IC are in low. That is the lowest current. So the average of these two is the ICC average. So these are some of the terms which you should know in the case of logic families.